B7, for the reaction mechanism below at 25 degrees Celsius, step 1 has one reaction rate, step 2 has a different reaction rate, and then step 3 has another reaction rate, right? So the first part of the question is, what is the overall net reaction for the mechanism, right? So if we look at it right here, so we have O3 plus NO forms O plus NO3. Step 2 is O plus O3 forms 2O2. And then we have NO3 plus NO forms 2NO2 in this case, right? So if we're looking at this right here, right, the first things that you always kind of like want to identify is, do you have anything that you would consider a catalyst? And do you have anything that you would consider to be intermediates, right? Because those things then are not going to be part of the overall, reaction in this scenario, right? So if we're looking at this right here, right, we have O3 is used here as a reactant once. It's used as a reactant in step 2. You don't see it anywhere in the products, right? So that's going to tell you that that's going to be a reactant. And then the next thing, right? So we have NO gas. So we have NO gas here as a reactant. Let me just delete these guys. In this case, right? And then we see it pop up here again, right? And so that's then also a reaction, right? So there's going to be 2 NO gas in that scenario. The next thing, right, is that looking right here, right? We have oxygen gas is produced. And then in the next step, right, it's consumed. So you would consider that to be an intermediate. So the oxygens, atoms, are not part of the overall reaction, right? Because they're produced and consumed, right? They're intermediates. Next, we have NO3 gas right here. And so NO3 gas in this scenario, right, it's produced in this reaction. It's not used in the second step. It's not produced in the second step, but we can see that it's being used up in the third step, right? So it's a reactant there, but it was produced previously. So that's also going to be an intermediate between those two, right? And so actually that's part B. So I'm just going to write out, right? So one intermediate is O gas. Another intermediate is NO3 gas in this case, right? So we have those two cancel out. Then going to the next line, right? We already know O3 is part of the reactants. We have then 2 moles of O2 gas that form in this case, right? And we don't see it consumed anywhere. So that's going to tell us that that's going to be a product. So 2O2 gas is formed. The next, right, NO gas we know is going to be a reactant. And then we also form 2 moles of NO2 gas in this scenario, right? So we have all these things right here. And so they all have the coefficients of 2. So we can just simplify that down and then just simply refer to it as that, B7. Right, and then the intermediates are NO3 gas and O gas. And so the next, right, which is the rate determining step in the reaction. So the thing to do is, in that case, we know what the K values are, and so we can look at them, and whichever K value, right, is the smallest one is going to be the rate determining step. So looking at them, right, K1 is 4.2 times 10 to the negative 5th, K2 is 1.0 times 10 to the negative 9th, and then K3 is 6.4 times 10 to the negative 14th, right? So the smallest K out of all of those, right, is the step 3 one. So that means then that step 3 should be the rate determining step in this case. And so part D, which I think also, again, might be one of the things that people are most interested in, is draw the reaction coordinate diagram for the reaction, label the diagram with each step and activation energy as well as the axes. And I realize I didn't put the activation energies in there, but that's fine. Right. And so if we're looking at it, right, we draw out our reaction progress. In this case, right, and then this is just simply energy. Right, we're going to have our starting materials right over here. And we know, right, we can assume that the reaction is going to form a more stable product at the end, right? So that should be lower in energy, right, for it to be spontaneous, right? It's not going to be spontaneous going upwards, right? So we already know that this product right here at the bottom is going to... Did it cancel again? Oh, come on, pen. We know that's going to be down there. Right. And so now the question is, how do you decide what the size of the humps and all of that stuff is? So the thing is, right, we've already talked about the Arrhenius equation in the past, right? But the reaction rate, right, K, or not, the reaction rate constant, right, K is equal to A times E to the power of negative delta A over RT. And so the larger the K value, the smaller the the activation energy has to be, right? Because that means then that reaction is going to go a lot faster. And so out of all of those, right, K1 has the smallest, the largest K value, right? So even though it's times 10 to the negative 5, right, it's still the largest, right? Because then after that, right, it's times 10 to the negative 9 and then times 10 to the negative 14. Right? But so you know that essentially what you're going to get is something that kind of looks like this right here, right? So this right here is the first step. This right here becomes step 2. And this right here becomes step 3. Right? And step 3 should have the highest activation energy, right? So that energy should be the highest up there out of all of them, because it has the lowest rate. Now, in terms of where those intermediate plateaus should be, right? Should it be above? Should it be below? You can't really tell from the data, right? And so that's why I didn't really make them dramatically different in this specific case right here. But what you can tell, right, is that the activation energies, right, this is going to be the activation energy for the first one. Oh, come on. Right, this is going to be the activation energy for the second step, right? And then this is going to be the activation energy for the third step in that case. Right, and so for the third step, right, that the maximum value should be the highest value out of all of them, and the activation energy should also be the highest out of all of them, in those cases. So, yep. But that's how you draw the reaction coordinate diagram, right? So if you just look at the K values and you can compare them, you can figure out which one's going to be the slowest step, which one's going to be the fastest step.